Okay, so today I'm talking with Greg Wilson, who is a restoration engineer who has spent over 13 years working directly with concrete, researching mixes, evaluating deterioration, and repairing failing structures. Greg's experience has given him a unique perspective that modern concrete is often over engineered, full of additives, and designed in ways that really shorten its lifespan. So, Greg's really on a mission to challenge the industry to rethink how we design and build with concrete. He questions our resilience on steel reinforcement, advocates for using materials based on their natural strengths, and believes that we should focus on buildings that actually stand the test of time. So, welcome, Greg. Thank you so much for being here. I'm glad to have you and to meet you. Maybe you could
Thank
start
you.
out by just telling us how you initially started in concrete and restoration work.
For sure. Based on your intro, I feel like I'm becoming increasingly like a heretic in the industry because of my opinions and
Yeah.
perspectives. Yeah, I want to explain all of that. My start in concrete, I have a lifelong love of concrete. My first job while I was in college actually was doing fresh concrete testing. So my hands have been in the concrete industry since I was 18 years old. So from my very first job in the industry, up until now has been all concrete related. So I'm very passionate about it. My mission in life is to make sure people are not saying cement sidewalks, but concrete sidewalks in addition to everything else. And I think the biggest thing is what I've seen in my 13 plus year career is that concrete is fallible. And I think we're led to believe that concrete is this pure, lifelong, super durable product. And unfortunately, that's not the case. So I think we need to sort of revisit what concrete can do for us.
Yeah, absolutely. And so when did you start kind of realizing that modern concrete might actually be less durable than some of the older methods? Like was there a turning point for you?
Yes. So my role as a restoration engineer is not as glamorous as it might sound. I'm not restoring historical buildings. I'm restoring and have for the duration of my career really practical infrastructure, parking garages, water treatment, wastewater treatment, infrastructure, sidewalks, those kinds of things that people use every day, but don't really think about it. In my career, I started questioning, well, we're repairing a lot of concrete. We are very busy repairing concrete. And
Yeah.
why? And what is the main thing that we're repairing? And yes, I live in Canada and it's a very harsh environment for exposed concrete, sure. But it seemed more and more in my career to be bigger than that, to be a larger problem that, and I sort of, the real crux of it that I sort of had an aha moment was I was restoring buildings that were 80 to 100 years old at the same rate as buildings that were 10, 20 years old. And that was
Oh,
really an
wow.
aha, eye-opening experience to me that this isn't just an old concrete problem. This is a holistic concrete problem in the industry.
Yeah, and new concrete that we're making today is not that quality. We still have to repair it
Yeah.
so soon afterwards. Okay. Yeah, that I didn't know that. Wild. Okay. And so at that point you just realized, okay, we're doing this wrong. And then did you started exploring alternatives and what were some of those first things that you kind of found?
Yeah, so I started sort of questioning how we were building to begin with, and because of the work I was doing, I was fixing existing structures. Although I'm technically on paper a structural engineer, I wasn't
Okay.
designing high rises. I wasn't designing parking garages from the bare bones. I was coming in once they had been in service and repairing them and fixing them for what was going wrong. And the biggest thing that I noticed, the number one sort of deterioration methodology of concrete is because of rebar. And that led me down this heretical path in the industry. And I actually just recently, just a few days ago, talked to a structural engineer about rebar. And I said, well, maybe we need to look at rebar differently. Maybe we need to not use rebar or design structures differently or use concrete in different ways that we don't need to use as much or any rebar. And he looked at me like I had three heads. That what a crazy idea. So
Yeah.
that was the biggest thing is like my sort of thought process and research was okay, rebar is a problem. How do we get away from that? And then we can look to history. And my favorite building of all times is a Pantheon in Rome, and it is 2,000 plus years old and still standing, and doesn't have a single piece of rebar in the ceiling, the roof structure of that building. And
Yeah.
so we've done it because I kept being told in the industry when I would talk to people about rebar is that, well, we have to use it and we've always used it. And that justification for what we are doing always drives me crazy. That just because we have done it for decades doesn't mean that it's necessarily the right path that we're going down. Second to that, I started seeing these crazy mix designs for concrete. Mix designs that had so many additives and superplasticizers and high early strength and various durabilities. And the concrete was not concrete anymore. It was, yes, cement and sand and aggregate and water, and then a bunch of other stuff mixed into it. We've been
Mm-hmm.
replacing cement in mixed designs, 15 to 20% of the cement we've been replacing with essentially reused materials, mainly silica fume and fly ash for decades. And we've been told that that's the right thing to do, and that's the good thing, and that's the green thing to do. But it really makes concrete not as durable from what I'm seeing in the industry.
Okay. Yeah, and I want to get into that a little bit more, but maybe in more simple terms, you could kind of define like, what is the difference between, modern concrete today and then traditional concrete that we used in like the Pantheon.
Yeah, for sure. So Roman concrete was super simple. It was lime. It was a pozzolan, which is a term that came out of the Roman era that we still use today, which is essentially volcanic ash, sand, aggregate, and water. So really simple recipe, like a very simple bread recipe is what concrete in my mind should be. So
Mhm.
it used lime as opposed to Portland cement that we use nowadays. It's sort of it's similar. Without getting deep into the chemistry of it, it's similar. Lime is kind of the more base material. Lime was more accessible. Portland cement now is made from limestone that's crushed and baked and made into cement powder, which is called Portland cement in the world, mostly in North America.
Mhm.
But Roman concrete, why part of why it was so strong and so durable was those pozzolans that were added into it, and that was like pure volcanic ash from the like Mount Etna and other volcanoes
Right.
in Italy and the Roman Empire, that had amazing strength capabilities. And it actually made the Roman era concrete completely resistant to any damage from seawater. So it made it a very durable mix, and we don't use that anymore. So now modern concrete, we use mostly cement, sand, aggregate, and water. But like I said, we add a lot of other stuff to replace cement because cement is expensive and hard to get and is a non-renewable resource.
Yeah, so just to go back, why do you think that we're not using that particular resource anymore? Is it just because of the little microclimate that had that
Mm.
volcanic ash and we just can't use that across the world?
Yeah, essentially that it was very
Yeah.
regionally based, and now concrete is so widely used that we needed a more commonplace recipe that
Mhm.
could be
Right.
used across the world. So,
Right.
essentially.
And then what are some of those things that you're saying are additives and maybe they're even marketed as sustainable,
Mhm.
but they're actually, making the material worse?
Yeah, so the big ones in North America are silica fume and fly ash. So silica
Mhm.
fume is a byproduct of steel production, ferrous steel production. And so it's
Mhm.
the ash that comes off of steel production. Fly ash is what it sounds like. It's the ash from coal production. But because there's less and less coal-fired power plants, there's less availability to fly ash also. So those are the two main ones. But because we've been using silica fume and fly ash, like for example, if we use silica fume, we need to add a superplasticizer to the mix in order to make the mix flowable and workable in situations. So
Oh.
we're using a byproduct material, which was all framed in this sort of sustainability lead driven, I'll call it greenwashing of the industry.
Mhm.
But because of that, we had to use a lot of other chemicals and a lot of other additives in the concrete to make the concrete work like how it used to work before we started adding these admixtures.
Mhm. Okay. And what additives are there any additives that you see as appropriate to add or which do you not
Mhm.
recommend people add?
Yeah, so I mean, I'm like a go back to the basics kind of guy. We're seeing like again what I'm sort of seeing with these nouveau mix designs, and a concrete supplier recently told me that they were bragging because they had over 2,000 mix designs that they were offering clients, and I was like, but maybe we only need two, maybe four.
Yeah.
We don't
Yeah.
need 2,000 options with all these different chemicals and additives in it. So saying that, I'm just sort of a go back to the basics kind of guy. So one of the ones that I've loved for a long time, and actually I did a research project way back when I was in college for a concrete class I was taking, and that's metakaolin. So it
Uh-huh.
is a baked basically version of kaolin clay, which is super popular. Kaolin clay is used in basically every cosmetic.
Mhm.
It's used in pottery, in porcelain. So it has a wide
Cool.
range of uses. Mining it isn't as difficult. It basically is just clay that is on the sides of mountains. Actually, in Canada, there's an area called the White Hills, and that's all kaolin clay. And that's where this company that's local here makes metakaolin. What I also like about it is it makes the concrete slightly lighter, which is better for urban heat effect. And also, you can dye the concrete internally better with a lighter original mix, whereas silica fume makes it really dark gray, for example.
Uh, I like that. I didn't know that. That's nice. A nice, like, aesthetic touch where you don't have to necessarily refinish
Exactly.
it. Yeah.
Yeah.
Awesome. Okay. Well, yeah. And so metakaolin, where do you mostly see that being used? Like, could you see that being used in like
Honestly, I don't see it.
foundations?
I have very rarely seen MX designs here locally, to be honest.
Okay.
Um, the industry is very much driven by the sort of the silica fume more so. Fly ash, like I said, less so just because there's less coal production, so there's less availability of it. So those are the ones that I see mostly. Metakaolin is usually only used in very specialty installations, regions, those
Hmm.
kinds of things. And this is why, like me as an engineer, I want to speak to the industry too to say like we should be looking at these sort of things more widespread, and we should be looking at how we can make buildings better from the very ground floor.
Yeah. Yeah. So you think that metakaolin as an additive could be kind of the future of concrete?
I think so. And I think the other future of concrete is being practical about how we're using concrete. I know like your video
Yeah.
that you had a few weeks ago sparked this in my head when I saw the headline "No more concrete." I was like, no, concrete is my life. But I agree with you that that we need to be using concrete in better applications. Concrete is amazing in compressive strength capabilities, columns,
Hmm.
walls, those foundations, those sorts of things. But concrete is not the all and the end all. And that was a big learning for me in the industry and sort of like coming to terms with my obsession with and love of concrete, but also looking at it practically. That we
Yeah.
use concrete for everything: sidewalks, driveways, bridge decks, girders,
Yeah. It's a
treat
lot of
water treatment,
concrete.
wastewater treatment, industrial applications, foundations, everything. Like we use concrete for everything. And there's a lot of rhetoric I'm hearing in the industry and from a sustainability standpoint that, well, like concrete's a problem. We're running out of sand, for example, like you've spoken about, um, the right sand for concrete. We're running out of cement potentially. And so what can we do as the industry? And the industry isn't, from my perspective, talking about, okay, well, maybe we don't use concrete for this or that application. Maybe there's a better product we can use. And that's what I loved about your video is your options that you provided people, that there's other alternatives out there than just using concrete for everything.
Yeah. Yeah. So, like, where do you think concrete can just not be used at all after watching that?
Well, it depends on application. So, for example, slab on grades. Like, I'll use parking
Mhm.
garages as a very non-sexy example. But a
Uh-huh.
slab on grade portion of a parking garage, it's susceptible to moisture, freeze thaw, chlorides from ice melt in areas that need that, salt water in areas that it might be exposed to that. And there's really no good way of restoring and repairing slab on grade concrete. I have looked at many a garage floor slab of friends and family where they have cracks everywhere. And
Mhm.
I tell them, like, unfortunately, the best fix is to remove and replace, which seems crazy and isn't really applicable. So I'm not saying that we need to go back to dirt floors, but maybe we
Okay.
need to look at other alternatives than using concrete where it's really hard to restore. There is amazing restoration techniques for concrete in slabs too, like suspended slabs, floating slabs, and higher levels of parking decks. For example, concrete's amazing in columns, like I said, and we have really strong repair techniques for that. So that's fine because it's durable in that capacity and we can fix it. Um, but maybe not, sidewalks, for example. Like sidewalks are exposed to so much wear and tear, and there's a lot of concrete. If you just think about how much concrete there is in sidewalks throughout even just North America, that maybe there's a better alternative product out there.
Right. Maybe even just pavers, permeable pavers that, yeah, can absorb the wash
Yeah,
off. Okay. Yeah, no, that's a great point. And I come from the residential side, so I'm not thinking about a lot of sidewalks, but yeah, I imagine there is a lot of that is unnecessary for sure. So I kind of want to go back
yeah,
to what you said earlier because I think that this is a really big topic is the rebar. You said that reinforcing steel, is what we use today for the most part. So can you explain why the steel rebar just causes so much failure?
sure. Yes. So I laugh and I joke all the time because I went to engineering school, I did all this education, and my first job out of university was hammer sounding and chain dragging, it's called. And you literally take a handheld hammer and you hammer concrete, and you can hear where the concrete is unsound. And that's what we call in the industry a delamination. So, me, like, puffed up chest coming out of engineering school, being told that I had to go and hammer sound and chain drag a parking garage was a very humbling experience. um,
I
so what
imagine.
happens is reinforcing steel and concrete work very well together, and it's one of the reasons why it's so widely used because the
Mhm.
properties of it naturally bond it to itself. The problem is reinforcing steel is embedded in concrete in many different directions, and inherently steel corrodes. When the steel corrodes, it expands and it pops itself away from the concrete, and that's when you hit it with a hammer or a chain, you can hear that pop between the
Mm,
rebar and the concrete. There's no longer a bond there. And then because there's no longer a bond there, it just sort of exasperates the deterioration. So water can get in there, chemicals can get in there,
mm,
salts from ice melt can get in there. And you've now made this like highway along the rebar in that plane between the rebar and the concrete where all of these materials can get into the interface of the concrete and then continue to deteriorate the concrete.
okay, yeah. And so what do you see as a viable alternative to rebar?
This is what I was talking to that structural engineer about last week. He said, "Well, we'll just use epoxy coated rebar." And I was like, "No, epoxy coated rebar is actually much, much worse than just traditional milled steel, reinforcing steel, because the epoxy coating, it's a green coating. I'm sure many people have seen
Yeah.
it on rebar. The problem with it is if you've seen any construction site, you know that when rebar is delivered to the construction site, they basically just throw it off the back of the truck onto the construction site. And now all of
Uh,
that beautiful epoxy coating that was done in a factory is chipped or cracked or has debonded areas of it. So now you've made that pathway, that highway of all the water and chemicals and everything directly against the reinforcing steel inside of the coating sort of. So
uh,
you've made it
oh,
even worse, and
okay.
then it can deteriorate. It actually, epoxy coated rebar actually deteriorates faster in concrete because of that mechanism, and then we have to fix it. So there's
Okay.
also talk about using fiberglass reinforcing, which again
Mhm.
is a viable option. It doesn't have that inherent bond with concrete, though, is one of the downsides of it. It's also quite expensive, quite difficult, and then we're using another plastic product in everything. So it seems sort of like a band-aid solution to me. So all this
Right.
being said, this is why I'm a heretic, because I'm coming to the realization that maybe there's no good reinforcing steel option.
Yeah. And how do you feel about because I have a friend who does vaulted brick arches and, kind of going back and forth with the engineer on whether rebar is actually needed or not. And in many
Mhm,
of these cases, it's just not. And if it's not regulated, then people go about it that way. But yeah, how do you see that in your eyes with the vaulted arch scenarios and how that
mhm.
could be structurally sound?
Yeah, I mean, again, it goes back to like those like base principles of design, like a mass construction with brick or stone or concrete block to create those really strong shapes. I mean, the Roman construction all throughout used barrel arches for everything because they were so strong and they didn't have reinforcing steel then. And all those
Mhm.
buildings for the most part are still standing. I mean, you look
Yeah.
at the Roman Colosseum or any Roman aqueduct, they all have that arch shape repeated, and a lot of times those are made with a combination of Roman concrete and stone or brick. And they, again, had no reinforcing steel and it worked. So the question of use of reinforcing steel and engineers going back and forth is another area of the industry that I have differing opinions on. We are so afraid in our litigious world that we over design everything to
Mm,
avoid litigious situations, to avoid failures, to avoid potential situations where you as the engineer or the builder are going to be sued. And because of that, the building codes are very intensive, and we then add safety factors of 50% or more, like 1.5 times
mhm,
or more to everything that we're
mhm.
designing to avoid those litigious situations. So in some cases, we might not even need reinforcing steel from a pure design standpoint, but we add it in to sort of cover thyself.
Right, right. Yeah, and so where in particular are we over engineering, do you think? Just in the rebar itself or
Everything.
everything? Okay.
Everything. And I think
Yeah.
this comes back to like a combination of everyone's afraid of getting sued and the litigious nature. And engineering by default follows you for life. So if you were to be an engineer that unfortunately was involved in a building that or a structure that collapsed or had issues, that follows you forever. And so it's a very scary
Yeah.
place to be.
Yeah.
So you inherently over design everything to further protect yourself as well. And then
Mhm.
this has implications of cost, this has implications of value engineering and so on and so forth. Like it's such a huge root problem, I think, that really is affecting the industry that we need to start looking at
Right.
holistically.
No, it's good to bring that to the
Mhm.
forefront. And so, like, if we removed steel, what kind of creative opportunities do you think
Mhm.
would be created out of that?
This is where I get really excited for because you look at the Pantheon, for example, in Rome, and it has amazing coffered ceiling that thins as it goes up to create the dome. And then it has the oculus in the middle, which is also an amazing feature. But the coffered ceiling creates ribs in the concrete that basically act as structural beams. So it doesn't have any
Mm,
reinforcing, but the concrete itself, with how it was designed, formed, and poured, creates a structural sort of rigidity to it. We have modern day waffle slabs, we call them in the industry. I think that's the technical term, but they're basically like a Belgian waffle floor slab, and it
uh,
has like a bunch of little ribs in it to create kind
yep.
of that coffered ceiling look. And you can buy forms of various shapes and sizes. And traditionally, waffle slabs didn't have any reinforcing steel in them either. So they're a great option to create instead of doing like a 6-inch slab, you maybe do a waffle slab that's maybe 18 to 24 inches thick.
Mm,
Architecturally, it has a lot of opportunities, I think, for really cool looking design. And then that's not even to mention like looking at designs inspired by nature. How is a leaf formed? Does a tree
right.
grow? Those kinds of things that I think structurally we can really look at and say, okay, what can we use there in structural engineering that doesn't use reinforcing steel? Because a tree is hundreds of years old
Yeah.
and doesn't have any
Yeah.
steel.
And so is there any data out there or studies out there that you know of that kind of take these biomimicry principles or take like the historic ancient, architecture to kind of help the validity, to
Right.
help engineers feel like they're not being held
Yeah.
liable for something? Like is there anything out there like that?
From my perspective, very, very little. Years ago, I did see a building, and I forget, I believe it was in Europe someplace, that was designed with some biomimicry in it, for the floor slabs and the roof slabs to be poured in concrete without any reinforcing steel. This sort of goes back to some fundamental issues that I also feel about engineering school and how engineers work, because a lot of
Mm,
design that we do now is based on software, based on spreadsheets, and isn't we're not going back to base principles and looking at, okay, how can we design these things or how can we be unique? A lot of the modeling software that structural engineers use, you can't even model things that aren't a square, let alone modeling things to design things that are the shape of a leaf. So it really
yeah.
comes back to engineers looking at like a very base a sort of principle of how we're designing things and how we're calculating things to get to that final design output.
Right. Well, yeah, the calculations alone. I'm kind of curious, do you think that with the evolution of AI that there'll be some opportunity for running these types of calculations to kind of give more merit to these new systems?
I think so. I think so, and I think that there's opportunities always driven through money. That I think if we can
Fair
prove
enough.
that we're using less concrete, it's easier to build, we don't have inputs from steel, that maybe we can drive the industry toward that kind of advancement. And I think in some ways it's like a reversion of going back to those historical understandings of how structures work that we need to do. I think we sort of need to stand here and look forward and backwards simultaneously to come up with the
Right.
best solutions and to really like holistically, fundamentally address some of these big problems we have. And I mean, this is something I talk to people all the time. Like, really, we have not changed how we build buildings for thousands of years. Like, from the fundamentals, we still build buildings the same. The construction industry is very slow to change. So let's
Mhm.
maybe like use this AI opportunity as a chance to look at things differently.
Yeah. Yeah, I don't think it's too far off. And in terms of calculations, I think that that would be really, really interesting to kind of gather all that data and find a way to make these structures a reality.
Yeah,
So I'm curious, when it comes to durability and sustainability, like in a lot of ways in today's world, like they're kind of polar opposites, or at least that's the mindset that people have. So how do you define durability and true sustainability in
yeah.
construction?
I like to use the term inherent sustainability, and that's sort of something that I've at least told myself
Okay.
in my work is that fixing a building is inherently sustainable. We're making a building more durable, we're increasing its longevity, we're making it last for further generations, and we're not just building quick structures. So
Mhm.
to me, I see true sustainability, inherent sustainability, part and parcel with durability and resiliency. We need to be building buildings that are not just, I use a school example. So where I live, they built like about 20 schools recently, and they were told that the schools only needed to have a 15-year lifespan because that's the lifespan of kids in a neighborhood going through the schooling system. And that just blew my mind that we are building and spending millions of dollars on design and construction and maintenance of a building for it to only last 15 years. So instead, let's build an amazing school that then maybe can be converted to apartments, maybe can become an office building, maybe can become something else. Let's change our perspective that we're doing a single use case for a building and design
Mm.
buildings that can ebb and flow. Like I think of the Salk Institute a lot as a structure that was purposely designed to ebb and flow. All of the mechanical systems and electrical systems are in this like void space between floors where the floor space of the building can become a lab, can become an office, can become an apartment, can ebb and flow. And I think that's how we need to be looking at buildings too. And so I
Mhm.
see that durability piece as being really front and center for true sustainability.
Yeah. Yeah, for sure. I love the restoration and multiple uses. And when you're talking about repairing concrete, what are the methods that are being used and how could those change?
For sure. Yeah, so it's pretty rudimentary, but it works. It's a tested, solution, um, with a caveat, with an asterisk, I'll explain.
Okay.
So, essentially, when we hit the concrete with a hammer or a chain and we find that a debonded, delaminated concrete, what we do, we mark it out, we saw cut the concrete down a few, maybe half an inch, and then we chip out all of the concrete with a camera. It's very labor intensive. There is some robotics and stuff in the industry that are doing some of this work. So we
Mhm.
do that on a slab, on a column, on a ceiling, everything. So it's very intensive because we have to expose around the rebar so that we can reestablish that connection between the concrete and the rebar. So once all the bad concrete, I'll call it, is chipped out, we abrasive blast or do hydroblasting or vapor blasting to remove all of the corrosion from the steel and remove all of the micro cracking that we've just created in the concrete. And then we pour new concrete back against it. Oftentimes, we
Oh, wow.
use cathodic protection to minimize future corrosion of steel. In some cases, we have to replace the steel and we have to lap the new steel with old steel, which makes the patches, the repair areas much, much bigger. And then we usually protect it with some sort of waterproofing. So that's how we repair it. It's worked. It continues to work. The asterisk part is it creates what's called the halo effect because now you have this new beautiful concrete with beautiful new or non-corroded reinforcing steel, and then right against it you have all the old stuff. So it creates this halo effect that now, in some cases, it exacerbates the corrosion of the non-repaired concrete faster.
Okay. Okay.
So it's
And
not perfect.
so, yeah, no, that doesn't sound great. Yeah. So, what, from your perspective, what do you think is the solution to that?
I think it's again, this works really well for current infrastructure, existing infrastructure that we can, these repair patches, if they're done properly, are lasting 25 plus years. So we're
Hmm.
we're increasing the durability and the longevity of these structures. And so I think it works for a lot of existing infrastructure. Where I see it is I'm talking myself out of a job here. But where I see it is that we
Hmm.
start designing things differently so that we are not relying on these repair strategies forever.
Hmm. Okay. And how do you feel about the self-healing concrete that's out there on the market?
Yeah, and I think all of these things are really interesting. I'd love to see them in a restoration kind of application because truthfully, every building that we have, the options for it are either to restore and increase its longevity or to demolish it. So I think we really should,
Hmm.
from a sustainability standpoint, look at restoration and reuse of buildings a lot. So all of these new materials like self-healing concrete, there was a study I saw from a university that was basically creating a structural coral, like a limestone-like material that was able to heal itself and grow stronger with exposure to CO2. So all those kinds of things I think are amazing opportunities that we need to sort of look at in the industry and find a way to package them as this is again solving an economic problem and solving an infrastructure problem.
Yeah, absolutely. So what do you think that, every engineer, builder, architect out there should know about concrete before they start specifying it, designing with it? Like what would be the one kind of takeaway that you would impart upon these professionals?
Yeah, I will never forget. I had a professor in my first year of college, and he was this old guy, and he took us down into a parking garage, and he showed us all of the cracking that was happening in a parking garage. And he said, "Healthy concrete cracks." And that
Oh,
is a statement that has stuck with me forever. So I think that is a big thing that people need to know. Concrete is fallible. Concrete is not the all and the end all. It has amazing applications, and when used properly, it has amazing strength and durability for potentially thousands of years. But we have to know its strengths and its limitations, and we have to use it appropriately.
right. So, if you're not designing with rebar and you're in like a seismic zone,
Mhm,
and it's cracking, like, do you have that in the back of your mind when you're designing or, well,
mhm.
when you're thinking about how these structures are gonna stand the test of time?
Yeah, and I think that is a big piece of where alternative materials play a part. I think back to traditional Japanese construction, for example, with wood and how they use all this amazing intricate wood joinery in seismic zones for exactly that reason, that the building can accommodate shifting and movement. And so that is an amazing use case for wood as a construction material.
Mhm.
Concrete can't move. When concrete moves,
Right,
it cracks. And
right,
so maybe concrete isn't the right material to be used on a large scale in very high seismic zones too. Or maybe we look at concrete, like foundations, concrete is really strong in. Maybe concrete foundations in a seismic zone that's really durable, connected to the earth. And then the rest of the structure, maybe we look at other materials instead of
right.
concrete.
So, when you think about, 3D printed homes,
Mhm.
what comes to the forefront of your mind?
I'm super excited about them. I think that they're
Yeah,
very interesting, and I think what I like about them is it brings in the options to do biomimicry, I think on a more accessible level, that you might not need to do really complicated form work if you can 3D print those kinds of shapes. I think is a
right,
really
the former.
interesting application for 3D
Mhm.
printing. I think the developments that are being done with 3D printing are really exciting. The one thing that I think is sort of a downside is that when we 3D print a structure and then we make it look like every other structure, I'm like, "No, let's embrace that it is different
Yeah.
and make it cool and unique." So I think 3D printing in part with that technology and looking at things differently. And maybe that's a method that we can test new design techniques also as with 3D printing. We can make scale models to test more easily and accessibly too. So I'm really
Exactly.
excited about 3D printing for concrete. I think it's a really, really strong application for it.
Yeah, absolutely. Yeah, and I think some people are playing around with clay mixes as well. So I think maybe a fusion between, what you were talking about with the metakaolin earlier, that
Mm,
could be really exciting. And yeah, in certain climates, right? It's just how how are we protecting the structure itself? And so yeah, probably these beehive shapes in very specific climates would work. I'm excited too. I think it's going to be interesting to witness moving forward for sure. Yeah.
definitely.
Yeah. And then do you have any other thoughts on like AI and the introduction of AI in the building sector?
Yeah, I'm cautiously optimistic. I think the adoption curve is super fast. And like I sort of mentioned, generally the construction and engineering industry is pretty slow to make changes.
Yeah.
Like you just look at the building codes that take 5, 10 plus years to make any sort of changes in the codes itself. The industry is really hesitant to do it. And yet I have seen really fast adoption of AI software in the industry from sort of a base layer, like maybe helping us with research, maybe helping us with some design questions. Widespread adoption, again, I don't want to work myself out of a job, but I do see some really strong use cases from an engineering kind of like the meat and potato of engineering. From a design base, I think it can offer a lot of opportunities. My fear is that we further lose touch with an understanding of what we are designing and how we are designing. And I think that becomes a piece that I can't quite reconcile in my head because I do feel that already design school has taken us away from traditional or authentic design practices and techniques that I don't want us to get further away from that still without maybe
Mhm.
seeing a strong benefit of it.
Yeah. Yeah. The education is going to shift for sure
Mhm.
in big ways as well. Yeah. This is kind of a random question, but if you were going to design your own home, this is kind of unrelated to concrete, but what would you build? What would you be excited to build if it were your own?
I do this every night. I design my own home every night. I have a piece of paper next to my bed that
Oh, wow.
it's like my, like, decompressing from the day. So I thought a lot about this. I love wood. I feel such a strong connection to nature personally, and I feel such a draw to be in nature and to ground myself and to have that connectivity with nature. I think it's so important for us emotionally and spiritually and everything to have that connection. So my dream home is like wood everywhere. I want wood ceilings and wood and huge expanses of glass, or ideally live in a place where I don't need a lot of windows and I can utilize natural ventilation. And then I want, like, concrete in there because it's my basis. So, have
Yeah,
a
that was a
foundation.
surprising answer.
Yeah, I know. I like the idea of, like, a foundation being built off of concrete. I think sort of metaphorically as well as strength-wise, I like
Mhm,
the idea of the house being built from, like, off of concrete, and then the rest
mhm.
of the materials being wood and being really natural and having that connection too.
I love that. I love that, and that's a great example of using concrete in the place where it matters the most,
Mhm.
especially if you're in, a seismic region, or if you're in the tropics, that type of design could totally make sense. Yeah.
Exactly, exactly. The
Cool.
concrete is so like, concrete block and concrete is, like, used everywhere in the tropics, I find. Everything is made from concrete block.
Well, for the durability, kinda going back to that and, termites being an issue as well with wood, and so I
Yeah.
think, again, back to, the longevity, durability piece.
And
Yeah.
I think that's exactly the piece, and, like, that was the takeaway that I took from your No More Concrete video is that there is alternatives out there, and maybe we need to look at pairing alternatives better in the industry too.
Mhm. Yeah. And having a diverse material palette with the buildings that we build instead of,
Absolutely,
a
absolutely.
monotonous concrete structure that we see in the
Yes.
cities. And I think
Don't
when I
even get me
titled that
started on drywall. That's a whole other
yeah, that would be
rabbit
a whole
hole of
'nother
mine.
video. Yeah, for sure. Yeah, and I think when I titled that video, it was more about You go to the cities and that's all you see. And so, advocating for a little bit more of diversity in the materials we use. Yeah. Amazing. Well, Greg, it has been great. If, as you move forward, like what are your goals? What are you it seems like you're very passionate about this and you want to get this out in the world. What's next for you?
Yeah, this has been a sort of a jumping off point for me to speak about this on a public forum. So thank you for the opportunity. I want to talk about these things to the masses. I really think it's important for people outside of the industry to understand what goes on in the industry too, and sort of like remove that veil of secrecy a little bit that exists, or that things aren't
Mhm.
really maybe as complicated as they might seem. And so I really want to do more videos, do more content creation where I can help educate and inform people and sort of bring a larger understanding to it. And then in the industry, I can do my work. I can talk
Sure.
to the professionals and the fellow engineers and designers and talk about these things, these hard conversations that no one's really willing to have, but to bring
Mhm.
them to the forefront so that the industry can start thinking bigger picture and differently.
Yeah, absolutely. I love the mission. Yeah, so where can people find you if they're interested in exploring these topics a little bit further? With you as the expert with all this information.
Mhm.
Yeah, where can people find you?
Yeah, my YouTube is at Libertas Talks, and I'm going to use that as a platform to talk about all sorts of different things that are in my head. I joke with people that I'm a generalist with really strong opinions. So I want to use that platform to talk about things like this, and technical things with my background and infrastructure, as well as just general design and kind of worldview things, because I think there's a lot of confluence and connectivity with a lot of these different topics too in our world.
Absolutely. Absolutely. Well, I'll link that in the description. And um, is there any parting words that you want to leave with us? If you had to sum up this conversation, what would you want to impart
Yeah.
upon the people?
Again, thank you for the opportunity. I
Yeah.
think the biggest thing is again my life mission about the cement versus concrete. We'll bring it back home to concrete.
Uh,
That cement is to flour what concrete is to bread. So that's my statement for
right.
the world.
Yeah. No, that's such a common mistake that people make. And yeah, it's good to know what's actually in the concrete.
Mhm.
Yeah, the ingredients that we're putting into this world ultimately. And yeah, making sure that we're thinking it not just in 10 years from now, but in 100, 200, I think we can go even further than that. When we look back in time, that it's possible to build really lasting structures. So,
Absolutely. And we should.
and we should, yes. All right. Well, thank you so much, Greg. It was great chatting with you.
Thank you. Thanks for everything.